Hello and welcome. In this video, we're going to look at general vectors. So in the previous lesson, we looked at vectors that represented displacement, and that was a measurement of some sort of distance. And therefore, if we summed two displacement vectors, we were able to find the total displacement or the net displacement. But we can represent other things such as velocity, acceleration, and force, among many other things. Vectors can also represent flow of some sort of stream or current. So let's take a look at an example where we're going to sketch some vectors, represent a scenario. Suppose we have a car that is moving at a speed of 45 miles per hour due north and a bike that is riding southeast. Assume this is 45 degrees in the respective quadrant. And the bike's going 13 miles per hour. Draw these corresponding velocity vectors and find their components. So the first thing that we want to do is we want to try to represent this graphically, as it's often easier to think about vectors when they are mathematized. So if we just represent northeast, southwest as the four directions here, four cardinal directions, we have a car that's moving at a speed of 45 miles per hour due north. Okay, so that vector is going to be pointing straight up vertically from the origin. Okay, and that's just one way we can represent it. We could put that vector anywhere we want, provided that it points upwards and it has a length of 45 miles per hour. So if we think about what this vector represents, this vector, and I will just go ahead and call this C for car vector, and this vector points 0 units to the right or left and 45 units straight up. So one thing to observe is that the magnitude of C, if we find that by taking the sum of the square of the components, we're going to get 45, and that's going to be in miles per hour. Now we often like to think about rate vectors in terms of displacement vectors. So if we think about this vector as representing the picture for 1 hour, we'll call this picture for 1 hour. Then we could think about this 45 as 45 miles. So in 1 hour, you would travel 45 miles north. The bike is riding southeast, so southeast is in this quadrant. We're assuming that that's going to be a 45-degree angle. So we'll represent that bike with a shorter vector, and the reason it's going to be shorter is because its speed is a lot less than that of the car. And perhaps we can call this the bike vector. And the problem with this vector right now is that we can't find its components quite as easily as we could with one pointing just strictly in the north direction. We have to think about what these components would be based on this angle right here being 45. So there we have a 45-degree angle. So if I take a moment and I just draw that picture of that vector, that's that same vector, and I triangulate this picture, and I know that this is my 45-degree angle right there, I also know that this is 13 miles long. Again, we're thinking about this as the picture over the course of 1 hour. So in 1 hour, that bike would move from the origin to the tip of that vector. So this is going to be 13. And to find what the x component is and what the y component is, well, for just a regular triangle, the sine of 45 degrees is going to equal y over 13. And the cosine of 45 degrees is going to equal x over 13. And so we could find y by saying that that's going to be the sine of 45, and x is going to be, 13 sine of 45, and x will be 13 cosine of 45 degrees. Now we also have to note that the y component of this vector is going to be negative. So here we're just resolving a triangle, but when we apply that triangle back to the coordinate system, we have to make sure we choose the right signs. So it's much easier to do this way and then just figure out what signs your x and y have to have by just solving and resolving a right triangle. So for the y comes out to about 9.2, and x comes out to be the same. This is a 45-degree angle, so the two sides are going to be equal, and so that's going to be 9.2 as well. So to actually write this vector, we would need to observe the fact that the x component is positive, since that's to the right of the origin, and the y component is going to be negative 9.2, since that's below the origin. And so there are the two vectors representing this scenario. If you wanted to, you could put this b vector at the tip of the n vector. It really makes no difference Perhaps maybe it would make more contextual sense if you drove in your car at 45 miles an hour for 1 hour, and then you took your bike at 13 miles an hour for 1 hour. So in 1 hour, riding 13 miles per hour in the southeast direction, you would displace 9.2 miles in the x direction and negative 9.2 in the y direction. So the velocity vector, something in motion, has a magnitude representing the speed of the object and a direction showing where the object is moving. So here we should also be able to observe that the magnitude of b, if we bound the square root of its components squared, it should not be surprising that this comes out to 13, because that is the length of the vector that we use to resolve the components. So again, the picture makes sense for 1 hour. It is still okay to say that this is 9.2 miles per hour and negative 9.2 miles per hour. That just means that's how many miles you're going to move in the x and y directions over the course of 1 hour. If you did this for 2 hours, you'd have to double the b vector. If you rode the car for 3 hours going due north at 45 miles an hour, you'd have to triple that car vector. So suppose we have a boat that's moving with velocity vector v, and we have that picture drawn here. It's moving 8 kilometers an hour relative to the water. Okay, so here it just appears that we're making that go due east. In addition, the river has a current c, so the c vector has a speed of 1 kilometer an hour. So you have a current that is blowing this way. So here's our c vector, and here's our v vector. And so when we sum these two vectors, we get a vector that actually is represented by this, I don't want to call it a hypotenuse because this is not a right triangle, but is formed by this third vector here. And we want to know what this represents. Well, we've already established that if we think about the 1 hour picture, over the course of 1 hour, the current should take you 1 kilometer in whatever direction that is, right? So its length is 1 kilometer an hour. We're not really told what the direction is, we're just given the picture. And the boat is going to move 8 kilometers this way. So what that means is if you sum these two vectors, you should end up wherever this point is right here over the course of 1 hour. In terms of speeds, if we're not going to think in terms of 1 hour, v plus c is the net speed, or excuse me, the net velocity vector due to the boat moving and the current moving the boat. So this is not exactly how it often works in physics, but it's a simple enough principle that if you sum together two velocity vectors, you get a net velocity vector. And the net velocity vector will tell you where the net velocity is moving in. So the net velocity vector would be this guy here. And so the boat would actually be moving along that vector because of the fact that it wants to move due east, but the current is sort of pushing it upwards. So if it just steers due east and continues to steer due east without changing its course, then the current will cause that boat to slowly drift upwards while the boat is moving east. This brings up a really valuable and important principle. And we can, before we get into that, we can also think about acceleration and force in much the same way. Force can be measured using different metrics, such as pounds of force. So for example, when you inflate your bike or car tire, you fill it to a recommended PSI, which is pounds per square inch. And you can really think about that as if you take a square inch inside your tire, there's going to be a bunch of pressure on the wall of this tire equaling however much pressure is inside of that tire, how much you fill it to. This is the amount of force measured in pounds applied to each square inch patch on the inside of the tire. In physics, force is often measured in newtons. We're not going to go into the specifics of newtons and what kind of unit of measurement this is, but you can do some research and see that newtons are used quite often. You can convert between newtons and pounds. So basically, newtons are, if you think about pounds, pounds are also relative to the acceleration due to gravity, and it just has to do a lot with that. So we're not going to go into that here. Suppose you tug of war with your dog, Frank. Frank pulls the rope with a force of 30 newtons. You pull in the exact opposite direction with a force of 50 newtons. Draw vectors representing this scenario. Describe what is physically going to happen over time if these forces remain constant. So in this case, we have to decide where we want those forces to point. They just have to point in opposite directions. So I could have one vector pointing this way as long as the other one points in exactly the opposite directions. The reason I don't want to do that, though, is because that's going to be a little bit harder to represent the components of those vectors. But if I represent these vectors on the axes, and I'm just going to choose to represent them on the horizontal axis. So I'm going to say that this is Frank over here. Frank's the dog, and Frank's pulling the rope in that direction with a force of 30 newtons. And so we can call this Frank's vector. And this is really easy to find. If it's 30 newtons of force due east, and we're measuring every component of this vector represents newtons, well, there's 30 newtons in the eastern direction, 0 newtons in the north direction. We can do the same thing for our individual, or with you, and this vector is just going to be a little bit longer because it's a stronger force. It's 50 newtons, and this is u, so we'll just call this the y vector. And the y vector has a x component of negative 50 because it's in the negative direction, 0 components in the y direction. Now, what we might speculate here is, since you're pulling harder on that rope than Frank, what we might expect is, if we represented the net force, we might think in net, you're going to be pulling that dog in the western direction. You're pulling with a stronger force, and it seems like that net force would be 20 newtons, since the 30 newtons would cancel each other out. If you and Frank were pulling with 30 newtons each, then the rope would in theory not move, since the forces are equal in opposite directions. But since you are pulling a little bit harder, we might expect that the net vector, or the resultant vector, net force, we might expect that that would be the vector negative 20, 0. That is, there's going to be a net force of 20 newtons in the western direction. Now, here's how we can verify this, and here's how we can justify this. When we solve problems using vectors, we make a very important, though primitive, assumption. If we have a series of forces or velocities or displacements that are interacting, then the net force or the net velocity or the net displacement is the sum of all the individual forces. So the net, note that we are summing vectors and not the magnitudes of the vectors. Here we kind of did that, but only because those were along the same axis. If the direction of those velocities is different, for instance, if you have a wind blowing at 45 miles an hour this way, and then you have a wind blowing, let's just say, 45 miles an hour this way, well, you can't really add 45 and 45 and say that it's 90. And that is because they're going in opposite directions. So in fact, these two vectors, if you added them together, let's just suppose that this one has a positive x and a positive y. This will have a positive x and a negative y. And when you add those together, you should get a 0 net force. Oh, sorry, this has a negative x and a positive y. So whatever this component is, negative x, positive y, this will be the same vector that's going in exactly the opposite direction, but a positive x and a negative y. And when you add those two vectors together, you're going to get 0, which makes sense because the two winds cancel each other out. So you can't add magnitudes, you have to add the vectors. In other words, if we have these force vectors, these individual forces, then the net force vector will be the sum of all those individual forces, which we're just calling F1, F2, all the way up to Fn. We could have as many of these as we want. So this also begs the question of, well, what if I know the net force, but I need to know one of these other forces on the right-hand side? As long as I can plug in all but one vector, I can solve for any unknown vector that I want. And that really is what is key behind this process. So consider again the tug of war with your dog, Frank. Frank pulls the rope a force of 30 newtons. You pull it exactly the opposite direction with a force of 50 newtons. What is the net force vector, and what is the net force? So in our net force vector, we've already established that 1 is going to point 30 newtons this way. And we said that this will be the vector 30, 0. This is Frank's force vector. And over here we have your vector, which is negative 50, 0. And if I want the net force is going to equal your force plus Frank's force vector. And that comes out to negative 50, 0 plus 30, 0, which gives me negative 20, 0. So as we had speculated, the net force vector is points 20 units in the western direction and is therefore going to have a magnitude of 20 newtons. So here's what our net force vector would look like. And we'll just try to draw it about 20 units long. And this is going to be the F net, which is negative 20, 0. And so it has a magnitude, which is pretty easy to verify. The magnitude of this vector is the square root of 20 squared plus 0 squared, which is the square root of 20 squared, which is 20 newtons. And so since all of these components are in newtons, the square root of the sum of the squared components is going to be in newtons as well. Let's look at another one. A plane heading due east at an airspeed of 600 kilometers an hour experiences a wind of 50 kilometers an hour blowing towards the northeast. Find the plane's direction and ground speed. So ground speed is just how fast is that plane going relative to the ground. So the first thing we're going to do is we're going to set up a picture. And there are a number of different ways you can set up these pictures. The goal is really just to, first of all, observe, okay, what is it that we're looking for? So the plane's direction, right? So the plane's actual vector, which we'll just call the net velocity vector, because we are dealing with velocities here, is going to be the sum of the plane's vector plus the wind vector. Okay, now we need to figure out the components of these. We can't add 60 and 50 because these are not in the same direction. If they were in the same direction, you could sum them. One's heading due east at an airspeed of 600 kilometers an hour. So 600 kilometers an hour due east will look roughly like that. Now I'm not going to worry too much about making this perfect. So this is the plane vector, and the plane vector is moving in 1 hour. If we set this picture up for 1 hour, it's going to move 600 kilometers due east. The displacement of this wind in 1 hour will be 50 kilometers, but it'll be in the northeast direction. So I could draw this vector in two different positions, and one of them is going to make more sense than the other. So northeast, and northeast we could assume is going to be 45, that's going to be 45 degrees in the first quadrant. And so this is going to look a lot shorter, and it's going to point something like that. And this is the wind vector. And its components we don't quite know yet, but we'll have to triangulate this. We'll have to triangulate this and think about this as being in 1 hour, this will be 50. This is our x, this is our y, and this is 45 degrees. So once again, we could do a little bit of right triangle trigonometry here and find out that this is 50 cosine 45 degrees and y is 50 sine 45 degrees. Those are going to come out to be the same, and that's going to be 35 point, we'll round it, we'll just keep it at about 35, and this is going to be in kilometers. Now this is going to be per hour, but since we're looking at this in a 1 hour picture, it makes a little bit more sense to most people to think about them as displacements. So this vector is 35, 35. These are kilometers per hour. That's how far we'll displace in the east and the north direction. As I had mentioned, putting this vector in a different location might make a little bit more sense because we're actually going to sum these two vectors. And so if I put that same vector right there, the way I can think about this is that the plane is going to move in 1 hour 600 kilometers east, but then the wind is going to displace that plane 35 kilometers east further and 35 kilometers north. So in this regard, I can think about this as the displacement of the plane and then the displacement of the wind. Now you could do the same thing by taking this plane vector and putting it on the tip of the wind vector, and it would still end up at the same terminal point. It would just form a gigantic parallelogram. So when you're saying, well, how do we know which one to put first, the plane or the wind? The answer is it doesn't really matter. We're just adding two velocity vectors together because we want the net velocity of the plane. And so to add those, and let me just go ahead and draw that vector here. So there's the v net that we're looking for. And v net is going to be the sum of these two vectors, which we just found to be 600, 0 and 35, 35. And so that's going to give us 635 and 35 as the v net vector. Okay, so once again, in the course of 1 hour, we would expect the plane to move 635 kilometers east and 35 kilometers north. And the extra 35 there is, again, just because of the wind. So we want to know its direction. So we want to actually find this theta right here. And to find that theta right there, let me just go ahead and once again draw the v-net vector. And this is the vector that has two components. We know that the x component is 635, and that's in kilometers or kilometers per hour. This is 35. And what we want to know is what's the length of v-net. And we also want to know what is theta. So to get the length of v-net, to see how fast that plane is actually moving in the direction that it's going, we just have to square root 35 squared plus 635 squared. And to get theta, we just take the arctan of opposite over adjacent, which is 35 over 635. And let's calculate those real quick. So this comes out to about 636 kilometers per hour. And so it's not moving much faster than it was before. That wind vector is not tremendously large. And then the arctan of 35 over 635 comes out to about 3.2. So this is going to be about 3.2 degrees. So that wind does not offset that plane very much. When we're working with vectors, it's important to have some semblance of properties of those vectors. And a lot of these properties will come as somewhat intuitive, that you can add two vectors in whatever order you want. You could do v plus w or w plus v. And that's pretty straightforward to see if you just think about it intuitively. If I were to have taken these two vectors and added them in the opposite order, 35 plus 600 is the same thing as 600 plus 35. And 35 plus 0 is the same thing as 0 plus 35. So we get the same answer both ways. Associativity just says for vector addition, if you're adding three vectors together, it doesn't matter which two you add. Again, we're just adding a couple of components. They're vectors that we're adding. They're not initially real numbers, but the way we add vectors is that we add the components in them. So that's just really a property of real numbers. If alpha and beta represent some constants, alpha and beta are constants, and the way you know that is because they don't have the vector hat over them, but also Greek letters often are used to denote constants. If you have beta times some vector and then alpha multiplies that result, you could just multiply the two scalars first and then multiply by v. For example, 2 times 3 times 1, 2. Well, I could take 3 times 1, 2 and get 3, 6, double that, which will give me 6, 12. Or I could just multiply 2 by 3, which is 6 times 1, 2, and that gives me 6, 12 as well. And so you can see we get the same result both ways. Distributive property says that, okay, if you have two scalars added together and then multiplying the vector, you could multiply the vector by alpha, multiply the vector by beta, and then sum the results together. And here's a standard distributive property. If you have a scalar that's going to distribute across the sum of two vectors, you can distribute it to v, distribute it to w, and you get alpha v plus alpha w. And then some of the identity ones, these aren't very interesting. They are really important properties, but they're not very interesting a lot of times. If you scale a vector by 1, you get the same vector back. That's called the identity property. V plus 0, if you add the 0 vector to any vector, basically remember the 0 vector is just a vector full of zeros. You add that to any vector, you get the same vector back. If you scale a vector by 0, you're going to get a vector full of zeros. And if you add -1 times v, that's the same thing as subtraction. So we can think about, the point of this property here is that we can think about subtraction as addition, where one of the vectors is being scaled by -1. So let's take a look at a couple more examples. We have 2 more to work through here. Suppose a motorized boat is moving 25 miles an hour at an angle of 45 degrees along a lake. Current pushes the boat 3 miles per hour at an angle of 120 degrees. Furthermore, a wind is blowing due north at a speed of 9 miles per hour. Find the velocity vector of the boat in the final direction it will be traveling. At what speed and angle will the boat be traveling relative to the ground after taking into account current and wind? The only difference between this problem and the previous ones is here we have 3 vectors that we're looking at. We have 3 forces, rather 3 velocities, and we already know that the net velocity vector is going to be the sum of all 3 of the vectors that we get. So we have a motorized boat, so we'll just say due to the motor of the boat, we'll refer to that as the m vector. And that's traveling at an angle there. Current pushes the boat 3 miles per hour, so we also have plus a current vector. There's some sort of current vector that we're going to need to find. And a wind is blowing due north, we'll just call that W. So if we take into account the fact that the boat has a motor that's causing it to go in a certain direction, and the current is also pushing that boat, and the wind is also pushing that boat, then the sum of those 3 velocities will give us the net velocity of that boat. So motorized boat is moving 25 miles per hour at an angle of 45 degrees along the lake. So think about a vector here, and since it says 45 degrees, we're going to assume that's in the first quadrant, since it doesn't say relative to what angle. So we know this is a 45 degree angle, and we know that this length right here is 25. So if this is 1 hour, this would be 25 miles of displacement. And that's what our m vector is going to, we're going to have to find the components of that to get the m vector. Current pushes the boat 3 miles per hour at an angle of 120 degrees. Okay, so now we have the current vector, and the current is going 120 degrees. So here's 90. This is 180, so 120 will be about here. And it's only 3 miles per hour, so we're probably going to draw that to be pretty small. And so this is going to be 3 miles of push in that direction over the course of 1 hour. And this is going to be an angle right here. Now this full angle is 120 degrees. This is 180. So that means this angle has to be 60 degrees. And that's going to be important to help us resolve that triangle. And so that's my current vector. And the wind is blowing due north at a speed of 9 miles per hour. So due north, 9 miles per hour. And draw that kind of short. And that vector right there is actually one that we already know, because if it's due north, it's pretty easy to find. Its magnitude is 9, so it's due north. That means it has no x speed and a speed of 9 miles per hour in the y direction. And there's our wind vector. So we already know that guy is 0, 9. To get the green vector, we're going to draw a little triangle. We know this is 45 degrees. We know this is 25 miles. So to find these 2 sides, x and y, x is going to be 25 cosine 45 degrees. Y is going to be 25 sine 45 degrees, which comes out to about 17.7. So about 17.7. So that means that since both x and y are positive, this is going to be the vector 17.7, 17.7. All right, so now we have 2 of the 3 vectors that we need. We still need the current vector, which is this guy here. So we'll just go ahead and draw a picture of that. Again, we don't need to worry about the signs of the components until we've resolved the triangle, and then we can apply signs, which makes things a lot easier. 60 degrees there. This is the x, this is the y. So cosine 60 is x over 3. So x is 3 cosine 60 degrees. And y is going to be 3 sine 60 degrees. And that comes out to 1.5. Now, again, since this vector is in the negative x direction, now we can say, well, that x actually has to be negative 1.5, and that y is in the north direction, so that's going to be positive 1.5. And now we have all the vectors that we need in order to find the net velocity vector of the boat. So summing these three together, 17.7 plus negative 1.5 plus 0 gives us 16.2. And 17.7 plus 1.5, that's 18.7, 19.2. And 19.2 plus 9 is going to give us the result of 28.2, which tells us the speed that that boat is actually going to be traveling in the north direction. So if we plotted where this vector is, this velocity vector is going to be 16.2 units this way and then 28.2 units up. So in net, I don't know, let's just kind of draw it like that. This is going to be roughly the net velocity vector. So that kind of makes sense because the boat wants to go along the green vector, but you have the blue vector that's sort of pushing it out towards the northwest, as well as this wind vector that's also pushing it somewhat up north. So in effect, that boat is still predominantly going, because these two, the blue and the magenta vector are so small relative to the green vector that it doesn't displace the green vector that much, but it does displace it a little bit. At what speed and angle will the boat be traveling in? So once again, we just have to find the components, we have to find the direction and magnitude of this vector here. So to answer that final part, now we'll just go ahead and draw VNet, and this VNet vector we now know is 16.2 miles per hour in the east, 28.2 miles per hour in the north. Again, if we want to think about it over the course of just 1 hour, we can think about this as 16.2 miles and 28.2 miles. And so then we can figure out what that's going to be, which is the magnitude of VNet. And the magnitude of VNet will be the square root of the sum of those components squared. And then if that's theta right there, tangent of theta is 28.2 over 16.2, so theta is the arctan of 28.2 over 16.2. And finding those components tells us the boat is actually moving at a speed of 32.5 miles per hour, and it's moving at an angle of 60.1 degrees, which based on our picture makes sense. Our last problem here involves one where we have to take advantage of this formula, the fact that if we know, for example, what we want the net force to be, maybe we want the net force to act in a specific direction, then we can figure out what an unknown force has to be in order for that to happen. So this is applicable where you already have some sort of stationary forces being applied, but you need to apply another force, for example, to cause something to stand still. So the context here is that we're looking top down on an electrical pole that has been knocked down by high winds. We have 3 city workers using winches on their trucks to pull the top of the pole back upright and to stabilize it prior to securing it. One worker pulls the pole with a force of 500 newtons at an angle of 35 degrees, and another pulls the pole with a force of 800 newtons at an angle of 260 degrees. The pole is still not stationary, so a third worker steps in and pulls the pole in a different direction with different force. Ignore the vertical component of the force. So in other words, we're not going to worry about the z component. We're just going to focus on the northeast, southwest components of the poles. Assuming from physics that we want the force force vectors to have a zero net force, determine the direction and force needed by the third worker. So we want a zero net force because if something is going to be stationary, that means there is zero force applied to it. For example, the reason a car doesn't move when it's parked out front is because there's zero net force on it. There may be winds blowing, but the winds are stationary enough to keep the car from moving. And of course, the car is very heavy as well. So let's go ahead and draw what we know. So we know that we have one worker pulls the pole with a force of 500 newtons at an angle of 35 degrees. So that means that we have one force vector in the first quadrant. It's going to be about 35 degrees. And we'll just say it's about 500 newtons. So that's 500 newtons of force. And that's an angle of 35 degrees. All right, so we'll call that force 1. So that's the force 1 vector. The second force pulls the pole with a force of 800 newtons at an angle of 260 degrees. So 260 degrees, here's 180, 270 is here. That means that the second vector is pulling downwards with a force of 800 newtons. And we're going to be concerned not about this big angle here, but what this angle here is, always relative to our horizontal axis. You could also form a triangle here and work with that, but if we do it to the horizontal axis, then it keeps how we find x and y very consistent. And so we'll call this force 2, and then we'll think about this angle right here as being, this is 260, this is 180, that would be an 80-degree angle there applied in that third quadrant. So if we just let this pole, which now imagine that this pole is for a second upright, where's this pole going to want to fall? Well, it's probably going to want to fall this way because of the fact that the forces are, one of the forces is east, one of the forces is south, so it's going to want to kind of go more towards the southeast. So in all likelihood, we're going to need a third vector, F3, that's going to pull into the second quadrant. The beauty of this is that we don't need to worry about it. So we'll let the mathematics take care of it for us. So then we'll ask this question of what does F3 need to be? Okay, so if I add F3 to this, what that's going to give me is the net force, and I want the net force to be 0. So this is where zero vectors come in handy. So I want a 0 net force. I don't want the pole wanting to fall east or west. I don't want it to fall north or south. I want it to not move at all in any direction. So I've got to find, of course, F1. We got to find F2. And then once I know F1 and F2, I can do a little bit of algebra to find F3. So I'll draw F1 over here. And we'll again create a triangle. This is 500 newtons. Here's going to be an angle of 35 degrees. So I need its components. It's x and y. Cosine 35 degrees is x over 500. So x is 500 cosine 35 degrees. And y is going to be 500 sine 35 degrees. So 500 cosine 35 is about 410. And we can go ahead and round that because 409 point something, 409.6 is not that far off from 410 since these numbers are quite large. 500 sine of 35 is going to be about 287. And these are both in newtons. So that means my F1 vector is going to be the vector, both positive components, 410 and 287. My F2 vector is going to be resolved with this triangle. So I'm just going to draw a triangle that looks like this. I know that this angle right here is 80 degrees. And I know that this vector right here has a length of 800 newtons. So to find the x and the y, and now keep in mind that both x and y are going to be negative since that's in the third quadrant. But the way I'm going to resolve this, I'm just going to treat them as positive numbers, and then I'll worry about the sign later. So once again, cosine of 80 degrees is x over 800. Drawing this relative to the x-axis will just keep these measurements consistent. So x is going to be 800 cosine 80 degrees, and y is going to be 800 sine 80 degrees. And 800 cosine 80 degrees is about 139. And 800 sine of 80 degrees is about 788. So that makes sense. We should be able to see that there's more of a southern force than there is a western force. And so these components are going to be 139 and 788. What is unknown at this point is what should the components of F3 be? Oh, and I failed to put those negative signs on there. Since F2 is in the third quadrant, this should be negative 139 and negative 788. And I'm going to add this third vector. I don't know its components right now. For now, I can just refer to these as either x and y, or a and b, use some other letters. So to solve this equation, I just have to use a little bit of algebra. It is the case that 410 minus 139 plus x has to equal 0. So 0 equals 410 minus 139 plus x, and 0 equals 287 minus 788 plus y. Another way to do that is just to add these two vectors together and subtract it over to the other side. So 410 minus 139 comes out to 271. So I have 0 equals 271 plus x. So therefore, x has to be negative 271. And 287 minus 788, make sure I wrote that down right. 287 minus 788 comes out to negative 501. So negative 501 plus y has to equal 0. And therefore, y has to equal positive 501. And so that means that the force 3 vector is going to equal negative 271, 501. Now, I don't have to adjust for signs at this point. The signs already stand for themselves because that's the only way that these will sum to 0. So negative 271, 501 is right somewhere in between here, and that's going to be F3 is negative 271, 501. So the direction that I would now find for that vector and the magnitude of that force, so negative 271, 271, and 501, those are just the forces. Again, we ignore the signs of it. Here we could find this angle, and we want to find the magnitude of F3. So to find the magnitude of F3, how big is that force that third winch has to apply? That's going to be the square root of 501 squared plus 271 squared. And the square root of 501 squared plus 271 squared comes out to about 570 newtons. And the direction is going to be, let's see, so this angle, this theta here, is going to be, tangent of theta is 501 over 271. So that means that theta is going to be the arctangent of 501 over 271. Now this is just going to be the theta, that angle, but that's relative to the negative x-axis, so I'm going to have to adjust for the sine relative to the positive x-axis. So this angle here is about 61.6 degrees. But that 61.6 degrees is this angle here. This is 61.6 degrees. So if I wanted it from the positive x-axis, I'd have to realize that that's 180 degrees minus 61.6. That would be relative to the positive x-axis. So because it's saying always relative to the positive x-axis, we would take 180 degrees. So this whole angle here, right there, would be 180 degrees minus 61.6 degrees, which comes out to about 118.4. And that's relative to the positive x-axis. And that concludes solving some of these vector problems in general. You see that we can always think about them in very similar ways as we can with displacement. They just happen to be the case that if you're measuring velocity, you can always think about it as in a 1 hour picture. And with forces, it usually just makes a lot of sense that when we sum a bunch of force vectors together, we get a net force.